I want to take a few minutes and talk about one of the more, I think, confusing topics when we're looking at inverse trig functions, and that is the compositions of trig and inverse trig functions. So let me just write down a couple quick examples of the kinds of problems I'm talking about. So in a minute, we're going to look at something like this: the sine of the inverse sine of 1/2 and then the other kind of problem, you notice here, the trig function, or you can think of the inverse trig function as inside of the trig function, but we can also have it the other way around. The inverse sine of the sine of pi over 4. So I want to try and explain there are times when these kinds of problems are very simple because the answer ends up being what you start with. I like to call that like a shortcut, where it's almost like you look at the problem and right away you know the answer. Because in this case, shortcut doesn't always work. So when you look at a problem, you have to recognize from the start whether this is a problem where you can use the so-called shortcut or not. And this is all the kind of stuff that I will clarify and explain as you go along. So because these are different and we approach them differently, let's first look at this case right here. And as I initially explain things, I will start out by using special angles because it's easier to see the result. And then we will look at some problems where the angles are not special angles, but we can still, at that point, come up with the answer. And let me explain the principle of sort of trig functions and inverse trig functions. These sort of act like opposites, or they reverse each other. That's what inverses typically are. Let me give you an example in algebra that I think most of you have seen before. If I take the square root of 3 and then I square it, it's almost like when you square something, it's the opposite of taking the square root. So sometimes I like to think these sort of cancel out and you're just left with what's inside. I mean, if you flip it around, what if I had x squared? If I take the square root of x squared, you sort of think to yourself, when you take the square root of something squared, you're just left with sort of what's inside. So that's why, so for this first one, you might look at this and just think right away, I've got the sine of the inverse sine of 1/2, and since these are like inverse functions, just like square root and you square something, you think, oh, well, these cancel out. So should be 1/2. This is what, in this whole talk, I'm going to call a shortcut. A shortcut is an easy way to solve a problem by just sort of knowing a rule or some rules. So is this true? Does this work? Well, I'm going to say I thought about saying it works sometimes, but I'm going to say it works most of the time. And then in a minute, we're going to talk about the thing you have to check. You check this one thing, and that will determine whether this works or not. just to sort of prove what's going on here, since these are special angles, let's do this the long way. In other words, I'm going to look inside here. When you have an inverse trig function, so inverse sine of 1/2, I ask myself the question. First of all, I always teach when I'm doing inverse trig functions. A lot of times I'll write this because I'm reminding myself that an inverse trig function is actually going to be an angle. So the question I ask myself is, I need to go find an angle where the sine is 1/2. But now let's take a quick minute, very, very important, to talk about the restrictions on inverse functions. By that I mean, if we're ever looking for the inverse sine or the inverse tangent, so we're looking for an angle as our solution. Turns out, if this is like the unit circle, the solutions for inverse sine and inverse tangent can only be in the right half of the unit circle. So this is an angle of 0. Up here, we have pi/2 in radians. Now, what's also interesting, so I have a copy of the unit circle. When we first learned the unit circle, 0 radians, pi/2 radians, pi radians, 3 pi/2, 2 pi, right? So for instance, this angle down here is like 7 pi/4. Well, another thing they've done for inverse sine and tangent functions, down here, they don't call it 7 pi/4. Instead of, they choose to use negative angles. Remember, positive angles move counterclockwise. If you're talking negative angles, you move clockwise. So if this is 0, this is negative pi/4. So down here is negative pi/2. So whenever you're trying to find an inverse sine or an inverse tangent function, the angle has to be in the right half of this unit circle. And quadrant 4, we have to sort of change the normal notation, and we start using negative angles. Now let's just discuss it now since you're talking about it. The cosine has the same kind of restriction, except for the cosine, the restriction is, if you take the inverse cosine, the angle or the answer has to come from the top half of the unit circle. Now the nice thing is the angle notation does change, 0 here and pi here, so you have the normal 0 to pi angles. But the answer to an inverse trig function, the angle has to be somewhere in the top half of the unit circle. So, all right. Now let's go back to this problem. The sine and inverse sine of 1/2. I'm going to first figure out what the inside equals to. When you work these kinds of composition problems, if you work it out the long way, you always work from the inside out. So the inside, this is going to be an angle. So I ask myself, what's the angle where the sine is 1/2? And this is an inverse sine, so it can only be over here. Well, the sine is 1/2, if you recall, right down here at pi/6. Once again, hopefully you know the unit circle now, pi/6. That's why I use the sine. So basically, let's just do this for now since I'm solving this problem. We hope it's 1/2, but let's see what it actually is. So the angle is pi over 6. So now I say, what is sine of pi over 6? Sine of pi over 6 is 1/2. So for this one, you could say the shortcut works, right? You started out with 1/2 inside of this composition function. And when you're all done, the answer is 1/2. It's almost like the inverse and the trig function canceled out. Just out of interest, if I do let's look like a cosine, same idea applies. What if I have the cosine of the inverse cosine of square root of 2 over 2? Now I'm hoping that the shortcut rule works, because if I can determine it works, then right now I just write down the answer square root of 2 over 2. But because this is a special angle, I can do it the long way and see what it is. And after we do this the long way, there we're going to talk about when we can and cannot use the shortcut. So once again, this is an angle. I'm looking for the angle, and once again, since it's an inverse cosine, the angle has to be in the top half of the unit circle. I'm looking for the angle where the cosine is square root of 2 over 2. Well, that happens at pi over 4, right? So theta is pi over 4. So what I have now is the cosine of pi over 4. And what's the cosine of pi over 4? Once again, hopefully you know your unit circle pretty well. Here's pi over 4 cosine is the value of x square root of 2 over 2. And as it turns out, for this one, the shortcut would have also worked. In other words, from the start, I could have said, these two functions cancel out. Your answer is what you started with. So here's the question. Is there a time or when can we not use a shortcut? I put up here, I was referring to the shortcut. The shortcut works most of the time. There are times when the shortcut does not work. So the question obviously needs to be, how do I know? What do I check to see if I can use a shortcut or not? And the key is the starting number inside your problem. So for instance, this one, it's 1/2. This one's square root of 2 over 2. And here's the question you have to ask yourself. Every time you have a problem, now be careful now, be sure this is a problem where you're taking a trig function of an inverse trig function, right? So that's for this kind of problem. What you do, you're given the problem, you look at the number and you ask yourself the question. Is the number between -1 and 1? And you actually include the -1 and the 1. So basically drive a number that's between -1 and 1, including -1 or 1. If the answer is yes, then you just use the shortcut. If the answer is no, then you have an undefined answer. No. What's up with this? Well, if you think about it, let me just do an example. That's probably the easiest. How about this one? Sine of the inverse sine of 2. I should qualify this. Key to the shortcut for sine and cosine. Tangent, it's not the same rule, but for sine and cosine, this is how you check if the shortcut works. All right, so let's get this example. Let's do this the long way. So once again, this is an angle. So I ask myself, I need to go find an angle where the sine is 2. So if I go to my unit circle, once again, the sine is always the y value of these points. So I got 1/2 square root over 2 square root 2, 1, and then here, and then they go negative. What's interesting, you may not have realized this, whenever we use the sine function, the largest possible number for the sine function is going to be 1. In other words, 1/2 is like 0.5, square root of 2 over 2 is like 0.7, square root of 3 over 2 is like 0.8. The sine function reaches its maximum possible value up here, and it's 1. If you take the sine of an angle, it's never going to be larger than 1, never going to be smaller than -1. When you take the sine of an angle, it's always going to be between -1 and 1. So with that thought in mind, look at this. I'm looking at the inverse sine of 2. So I ask myself the question, I need to go find an angle where the sine of that angle equals 2. You know what? That angle doesn't exist. The sine function of an angle is going to be a maximum value of 1. So how can I go find an angle where the sine is going to be 2? I cannot. So therefore, if you have a problem like this, there's no solution. So it's actually very simple. With these kinds of problems, you simply look at the number. If the number is from -1 to 1, then you simply use the shortcut. If the number is not between -1 and 1, then it's undefined. So now, let's do a couple more problems where these aren't even going to be special angles. How about sine of the inverse sine of -3/5? With this kind of composition, you simply say to yourself, okay, here's my number. Is it between -1 and 1? Yes, it is. So right away, there's my answer. Let's do one more. How about the cosine of the inverse cosine of 0.8? So I look at the number. Is the starting number in here between -1 and 1? Yes, it is. Then I can use the shortcut. 0.8. The cosine of the inverse cosine of -4. I look at the number. It's a number between -1 and 1. No, it is not. So it's undefined. All right, hopefully not too bad. So what we've gone over now is this case where you start out with a trig function, and then inside is the inverse function. Now let's flip it around and see how we go about figuring out these answers. We're taking the inverse trig function of a trig function. And actually this is a little trickier. And we're going to see why as we talk about it. So let's once again start out with just one of a problem with a special angle and see what is happening and go from there. So how about if we were asked to solve this, the inverse sine of the sine of pi over 4. Once again, if I could use a shortcut, since I've got an inverse sine here and a sine here, I'm hoping they'll cancel out and the answer can just be pi over 4. Well, let's see. Let's do it the long way. Start from the inside out. Sine of pi over 4, if I'm a unit circle, I remember sine of pi over 4 square root of 2 over 2. So now the problem becomes the inverse sine of square root of 2 over 2. Once again, this is going to be an angle. So let's remember for the inverse sine, my angle can only be over here in the first or fourth quadrants, right? It goes from 0 to pi over 2 and down here to negative pi over 2. So I'm looking for an angle along here where the sine is square root of 2 over 2. And I realize the sine of pi over 4 is square root of 2 over 2. So therefore, this is going to be pi over 4. And it looks like, in this case, the shortcut worked. Great. All right. Let's look at a second problem. How about the inverse sine of the sine of 3 pi over 4? So working from inside out, I'm hoping it would be nice if this equaled 3 pi over 4. If the shortcut worked. Well, let's see. Let's work it out the long way. Sine of 3 pi over 4. If I go back and think about my unit circle, sine of 3 pi over 4 is square root of 2 over 2. So now I have the inverse sine of square root of 2 over 2. So now, once again, inverse sine, just to make it very clear, I don't get confused. This is going to be an angle. So looking for the angle where the sine is square root of 2 over 2. And once again, the angle has to come from this right half of the unit circle. So where's an angle here where the sine is square root of 2 over 2? Actually, pi over 4. So here's a case where the inverse sine of the sine of 3 pi over 4 is pi over 4. So in this case, the shortcut did not work. So what's up with that? Well, here's a simple question I ask, or the thing I check to see if the shortcut works for these kinds of problems. So I'm first given this problem, I look at this angle in here and ask the question, is the original angle in the, all right, I'll explain this, in the OK region. OK region means I'm thinking of this inverse sine And wherever the inverse sine is defined is what I'm calling the OK region. So in other words, if I start out with pi over 4 here, then yes, the original angle is in the quote unquote OK region. If I looked at 3 pi over 4, 3 pi over 4 goes over here, and it's not in the region of my inverse sine function. So that's what I mean by the quote unquote OK region. So now, if the answer is yes, then you can use the shortcut. And for these first two examples, this first problem, so here it is, pi over 4, is it in the OK region? Yes, it is. So I can use the shortcut, and I can just right away say this whole thing, they cancel out, and you're left with what's inside. However, if the original angle is not in the OK region, then you have to go use reference angles. Okay, so this is where it gets a little confusing. So first of all, our check. For this problem, my original angle is 3 pi over 4. I realize 3 pi over 4 is over here. It's not in my inverse sine region. So the answer is no, you cannot use a shortcut. And you can see here when we did this problem the long way, the shortcut would not have worked because the answer is pi over 4. But let's figure out how we know this answer is pi over 4, especially if we're given angles that are not special angles, if we cannot in our head do this calculation. So here's where it gets a little confusing. So here's what you have to do. Let me go ahead and let's go into this example of 3 pi over 4. So I'm given this problem. I go look at my original angle and I say, so for the inverse sine, I know I want to see if my original angle is between negative pi over 2 and pi over 2. And I realize it's not, it's over here. So then I sort of say, okay, I can't use a shortcut, but instead I have to figure out my answer by using reference angles. Now, quick review about reference angles, right? Reference angles are, you have an angle. Here's my 3 pi over 4 angle. Reference angle is always the angle, the shortest angle back to the x-axis. Could be the negative x-axis, could be the positive x-axis. That's what the reference angle is. So in this case, for 3 pi over 4, the reference angle, if you think about it, this is 0 and this is pi, or I can also think of pi as 4 pi over 4. So if this angle is 3 pi over 4, and this is 4 pi over 4, what's my reference angle? Pi over 4, right? That's a pi over 4 angle to get me to the x-axis. So then what you do is, based upon the reference angle, you go in to the allowed region and you find the two reference angles that relate to my original angle. So here's an angle, reference angle is pi over 4. So the reference angles for this angle is going to be right here, pi over 4. And then down here at negative pi over 4, because that's a pi over 4 reference angle. That's a pi over 4 reference angle. Now, if you remember, The reason why we're using reference angles is because from way back, we talked about reference angles. When you take the trig function of a reference angle, they all have the same number result. The only difference might be whether it's plus or minus. So all three of these angles, the trig function is going to be the same number. The only difference might be whether it's plus or minus. So therefore, what happens is, since my original angle is sort of like outside of the allowed region, I have to sort of switch, and it's like this original angle gets converted to one of these reference angles. One of these reference angles is going to give me the correct answer for my original angle. So the question is, well, I've got two possibilities. Like in this case, I've got pi over 4 or negative pi over 4. What would be the correct answer? Well, the key is, once you have two possible reference angles for your solution, you have to look at the plus and the minus. My original angle, this is a problem with sine. My original angle is in quadrant 2, and I'm working with the sine. So that means I know over here, the sine's positive. Now, if I look at my two reference angles, I know this reference angle here, quadrant 1, is a positive, and this reference angle over here would be a negative. Therefore, I want the signs to be the same. So this is positive, this is positive. Therefore, this is going to be the reference angle that gives me the exact same answer as my angle over here. And that's how I end up saying that it's pi over 4. Let's do a problem where it's not a special angle. How about the inverse sine of the inverse sine of the sine of 4 pi over 5. Let me draw a new circle here, because we're going to have to do some work over here. Here is my allowed angles for inverse sine. So the first thing you have to do on all these problems is you have to find your angle. Okay, let me emphasize that. You have to find your angle. Up here, first thing I did, I found my angle, pi over 4 is right here. And then I was able to answer the question, is this in the OK region? And yes, it was. Therefore, I could use the shortcut. The next problem, 3 pi over 4, I had to first find that angle. I saw it here in quadrant 2. And I asked myself, is it in the OK or allowed region? The answer was no. So then I had to go in and look at the two reference angles that were in the allowed region. Now, those first two problems were special angles. This is a little trickier because this is not. This is in 4 pi over 5. But it's key. I still need to figure out where 4 pi over 5 is, at least what quadrant it's in at a minimum. So if you think about it, when you have sort of funky angles like this, sometimes it helps if we can convert our angles here on our graph. So 0 is 0. If all the way over here is pi, but I want to write that angle with a 5 in the denominator. And hopefully you can see that pi is the same as 5 pi over 5. And then what would pi over 2 be the same as? Well, here's the way I think about it. pi over 2 is halfway between 0 and pi. Halfway between 0 and pi, or you could say halfway between 0 and 5 pi over 5. Half of 5, so you can think about it as you've gone 5 pi over 5. Half of that is going to be like 2.5. You can almost think of pi over 2 as 2.5 pi over 5, right? If from here to here, if I'm looking at, I'm assuming 5's in the denominator. From here to here was 5 pi. Cut it in half, has to be 2.5 pi. Where's 4 pi? Well, obviously 4 is bigger than 2.5 and less than 5 pi. So my guess is 4 pi is here in the second quadrant. So now, first step is always find your angle. Second step is ask the question, is my original angle inside my OK region? And it is not. So therefore, for me to get the answer, I've got to go ahead and find my reference angle and find my reference angles that are inside the allowed region. So once again, the reference angle is shortest distance to the x-axis. Now, if this is 5 pi over 5, and this is 4 pi over 5, hopefully you realize that this must be pi over 5. And then beyond that, we have to look at these reference angles on the right half of the circle. So basically, pi over 5, negative pi over 5. So my original angle is outside the allowed region. I go find the two reference angles inside the allowed region. And then I say which one of these has the plus or minus that I want. Well, if I'm doing the sine and I'm over here in quadrant 2, trig function is going to be positive. Of these two reference angles, this one is going to have a negative sign. This one's positive. So that's why I now say the answer is pi over 5. So let's repeat those steps again. You go find your original angle and you ask yourself, is that angle in my allowed region for inverse trig functions? If it's not, if it is, then you use your shortcut and you're done. If it's not, then you have to go and find the reference angles that will be inside the allowed region and then figure out which one is correct. Let's do another sine, then we'll do a couple of cosine. About the inverse sine of the sine of 3 pi over 5. First thing I have to do, I have to go graph and find this angle. It's a negative angle, so I'm going this way. Once again, if I think of it like that, 0 is here, negative 5 pi over 5 is here. Then here's negative 2.5 pi over 5. So negative 3 pi over 5 is maybe in here somewhere. So my original angle was not in my allowed or OK region. So therefore, I'm going to have to go find the reference angle for this original angle and then go find the reference angles and on the right half of the circle to find an answer. So if this is 5 pi over 5, oh, this is -5 for this problem, -5 pi over 5. So if this is -2.5 pi over 5, actually here from 3 pi over 5 to 5 pi over 5, it's actually pretty straightforward, right? It's 2 pi over 5. So therefore, -2 pi over 5, and this is actually -2 pi over 5. And up here, 2 pi over 5. So two possible reference angles. Once again, because my original angle, -3 pi over 5, is not within my allowable transfer function regions, I have to look at the reference angles. So this is a possibility, and this is a possibility. Now the sign down here in quadrant 3, the sign is always going to be negative. These two reference angles, what's the sign going to always be up here in the first quadrant? Positive. What's it going to be down here in the second quadrant? Negative. So these match up. So therefore, the answer to this must be -2 pi over 5. So a little tricky, Let's do a couple cosine problems. Of course, with the cosine, start with a special angle. Same steps apply as the sine, except once you look at your original angle, now you're looking to see if it's in the top half. If it's in the top half, then you use a shortcut. If your original angle is in quadrants 3 or 4, then you have to use your reference angles. So this one, 2 pi over 3, we know 2 pi over 3 is right about here. It's actually in my allowed, or my okay region. Therefore, I should shortcut it, I'm done. How about this one? Oh my, I'm so sorry. I didn't see all that. This was my first problem. My angle was 2 pi over 3. Since it's in my allowed region, I can use a shortcut and just right away see that these cancel out. That's 2 pi over 3. Now I'm looking at 7 pi over 6. 7 pi over 6 is right about here. So this original angle is not in my allowed or okay region for inverse cosine. So what I do is I'm going to go find the reference angles in quadrants 1 and 2. And the way I find the reference angles is I go to my original angle. If this is 0 and this is pi, you might want to think of it as 6 pi over 6. So really, what's the reference angle is going to be pi over 6, because you've gone from 6 pi over 6 to 7 pi over 6. So if I draw the two reference angles in my allowed region, I'm going to move pi over 6. So this is going to become 5 pi over 6. And then my other reference angle, pi over 6. Now down here, my original angle in the third quadrant, I'm looking at cosine. Is cosine going to be positive or negative? Actually, cosine is negative down here. So which one does that correspond to? Should I go up here to pi over 6, or over here to 5 pi over 6? Well, pi over 6, cosine's positive. 5 pi over 6, cosine's negative. So I got to go where the signs match up. So therefore, the inverse cosine of the cosine of 7 pi over 6 equals 5 pi over 6. So once again, let me just state it again. I do another couple, maybe cosine examples. For either sine or cosine, first thing you do is you go find the original angle. If the angle is in your allowed regions, then you're done. You can do the shortcut. But if the angle is outside your allowed regions, then you go ahead and have to find the reference angles in the allowed regions. And once you find the reference angles in the allowed regions, then you just have to determine whether it's plus or minus. So I do a couple of cosines where they're not actually special angles. Inverse cosine of the cosine of 4 pi over 5. First thing I'm going to do is I'm going to try and make a rough sketch of this 4 pi over 5 angle. 0 pi, or I think it's 5 pi over 5. So 4 pi over 5 must be, this is like 2.5 pi over 5, halfway. So it must be maybe somewhere over here, where the reference angle is going to be 5. Now, since this is a cosine problem, oh, I'm sorry. I misspoke. For this one, it is in the allowed region. I don't even need to find the reference angle. Sorry. I should have drawn my allowed region in right away so I don't get confused. So this is actually in the allowed region. So no need for reference angles. You're pretty much done. Let's do one more. Hopefully I won't get confused. Inverse cosine of cosine of 11 pi over 7. First thing is find your angle, see if it's in the allowed region. And don't be confused like the last problem. So here's the allowed region. Where is 11 pi over 7? Well, if I think about it, pi is here. I can rename that 7 pi over 7. This is 2 pi, or 14 pi over 7. Halfway is 7. So this from here to here is 7 pi. Half of that is 3.5. So if I add that here, this is like 10.5 pi over 7. If we can see that, right? Because from here to here is 7 pi over 7. Half of that would be 3.5 pi over 7. So this angle here, if I add 3.5 to 7, I get 10.5 pi. So therefore, 11 pi over 7 is right about here. Now this definitely, this angle, this original angle is not in my allowed region. So therefore, I'm going to have to go use my reference angles to find my answer. So the reference angle, shortest angle back to the x-axis. In this case, now you can see I'm going from 11 pi over 7 to 14 pi over 7. I would have to go 3 pi over 7. So if I look at reference angles, if I go 3 pi over 7 here, and then here, three pi over 7. If this is 3 pi over 7, this must be 4 pi over 7. So my two reference angles, 3 pi over 7 and 4 pi over 7. Now I need to figure out which one has the correct plus or minus. My original angle is on here in the fourth quadrant. In the fourth quadrant, we're looking at cosines. The cosine is positive. So I want my reference angle to be a positive angle. And 3 pi over 7 is positive, 4 pi over 7 is negative. Therefore, it looks like this should be 3 pi over 7. All right, so final summary. We have these two types of composition problems. And the first one I covered, I think it's much easier. So when you start with a trig function, so you have a trig function of an inverse trig function. All you do is check the original number. If it's between -1 and 1, the shortcut works. If it's greater than 1 or less than -1, then it's no solution. One's a little trickier is when you start out with the inverse trig function and then inside is a trig function. My suggestion here, how to figure this out, is you look at that angle immediately and go find out where that angle is. When you find out where it is, if you have a sine problem, then you see if that angle is inside the allowable region for inverse sine. If it is, then you're done. Use shortcut. So for pi over 4, it's over here, it's inside the region. You give the numbers, you're done. However, if the original angle is not in the allowable, so the second step I did here was like 4 pi over 5, or even 3 pi over 4. So 3 pi over 4, I guess I wrote it up here. 3 pi over 4 is right here. It's not in the allowed region. So therefore, what do? I have to somehow, it's like I have to move this answer from over here into my allowed region, either quadrant 1 or 2. The way I do that is I find the reference angle from original angle. In this case, it was pi over 4. And then I look at the reference angles in my allowed quadrants. So pi over 4, negative pi over 4. And then I check and see which one of these reference angles has the same plus or minus as my original, and that's the answer. So you can see how, a couple more examples here, 4 pi over 5, graphed it. It's definitely not in the allowed region, so I have to go get the reference angle, which is pi over 5, and use that to create two reference angles over here, 2 pi over 5 and negative 2 pi over 5. Oh, sorry. I've done multiple problems on this one. So 4 pi over 5 is the pi over 5. So you've got, wow. I did 2 problems on here and I keep going back and forth. So let me just take a step back. Maybe jump to my cosine examples where I'm not going to be confusing you. I'm trying to just summarize. Let's do this one. Cosine of 4 pi over 5. Here's my original angle, 4 pi over 5. It's in my allowed region. Boom, use the shortcut, you're done. 11 pi over 7. Here's the original 11 pi over 7 angle. It's not in my okay or allowed region. Therefore, I go find the reference angle. I found the reference angle to be 3 pi over 7. Based upon that, I go plot the 2 reference angles in the allowed region. 3 pi over 7, 4 pi over 7. I say, well, which one of these is the answer? Well, it's the one with the same plus or minus as my original angle. Since it's a cosine, down here quadrant 4, cosine of quadrant 4 is positive. Cosine of quadrant 1 is positive. Cosine of quadrant 2 is negative. Therefore, it's the angle in quadrant 1, which is 3 pi over 7. And that's why this is the answer. All right, hopefully as you think about this and do some problems on your own, it'll become clear to you and you can pretty easily be able to figure these out.